I'm going to be going over problem set number 7, which goes over chapter 10. First question says that the difference in chemical potential for a specific molecule between region A and region B in an ideal dilute solution, so emphasis on ideal dilute solution, is 7.5 kilojoules per mole. Region B has a higher chemical potential and a concentration of 200 millimolar. Suppose that over time, regions A and B equilibrate with one another. Do you expect the concentration of A or B to increase? So you're going to want to think of this as a certain region A. Let's see. We have region B, so region A and region B. So this is going to have a higher chemical potential and a lower. So we're going to denote this as B being larger than A. And we know from the chapter reading that spontaneously the higher chemical potential will go to a lower chemical potential, which energetically makes sense from the definition of chemical potential, since chemical potential is just the density of free energy, and that density is going to want to be spread out. So from this analysis, we can determine that A will increase in concentration. The next part of the question is, what is the concentration in region A at 300 Kelvin? So the equation we're going to use is the change in chemical potential is equal to RT natural log some potential over another potential. Now we are going to want to be solving for A. Maybe it's better to denote it with each region. So we know all these except for C sub A, and we're just going to flip things around. So maybe I won't do everything in one step, but it's going to look something like this. And then what you're going to want to do is exponentiate both sides. So it's going to take care of the natural log. And then we can come up with an expression for the concentration of A. So since we're given the concentration in region B, and we know that it has a greater chemical potential than A, that's why we put it in the numerator and not in the denominator. And we're just going to plug in these values. And let's see, 7.5, and this is kilojoules. It's at 300. You could maybe use 2.5 kilojoules per mole, but just for completeness, I thought I'd do the written out version. Either way, you should get something like this. Okay, next question states that recall that a chloroplast is composed of a matrix space and an inner membrane enclosed lumen. Suppose that in the light, chloroplast maintains a luminal pH of 4, while the matrix is at pH 8. Ignoring anything associated with charge, calculate the difference in the molar chemical potential associated with this concentration difference at 300 Kelvin. So this is just using the same equation as above, where now we're going to be using the pH as our different concentrations, since by definition pH is just the negative log of the ion or proton concentration. Let's see. So that's going to be the following. And you get this answer. I converted the number to kilojoules just because it's more manageable. The same reason why this is in millimolar. But of course, that's your preference. The next part asks us, recall also that this concentration gradient will eventually be used to drive the production of ATP. What does this value you have obtained say about the stoichiometry of protons required to synthesize ATP? So I believe it's the change in free energy of ATP hydrolysis. It's going to be negative 28. So that's kilojoules per mole. Can't forget units. That means that ATP synthesis is going to require 28 kilojoules per mole. And the number we obtained previously, so we've taken the magnitude, 22.93, it's going to be less than 28. And that means that we're going to have to use more than just one proton to power ATP synthesis. Otherwise, we're not going to have 28 kilojoules that are required to make ATP. So, okay. Question 3. Circle the correct answer for a reaction with a large delta G compared to a reaction with a small delta G. The reaction with a larger delta G is always the faster reaction. The reaction with the larger delta G is always the slower reaction. The two rates are equal, and it is impossible to decide which reaction is faster. So you might recall that for a reaction to take place, it's going to have to overcome some activation energy. And activation energy, in this case, is not directly related to the change in free energy. So we'd have to be given some information on concentrations or activation energy. And for that reason, that delta G just isn't going to be enough information. So D is going to be the correct answer. Okay. At equilibrium in a test tube, the concentrations of GDP and inorganic phosphate are following, while GTP is 80 micromolar. What is the equilibrium constant of the following reaction? So equilibrium constants are going to be the concentration of products over the concentration of reactants. And looking at the reaction equation, we come up with the following. So you just plug in those values that you're given. Let's see, so 1.99992. Square that just 2 times. And then 80 to the negative 6 is what a micromolar is. I converted that into molar just because we want to be working with the same units. And solving for that, you will get the answer for KQ. I'm not going to do the calculation entirely just for the sake of time. Then part B, you want to calculate the delta G, the change in free energy of the reaction at standard conditions. And temperature is going to be 298 Kelvin. So we also want to know that the above values are not temperature sensitive. So what that tells us is we're going to use the following equation, which might look kind of similar to what we're working with earlier, and just plug in those values. Should get 8.314, which is our gas constant, 298 Kelvin, and then whatever you calculated above. So that number. Okay, the concentration of intracellular GTP has been measured for E. coli growing in normal laboratory conditions to be 5 millimolar, while GDP is 0.7 millimolar, and inorganic phosphate is 10 millimolar. What would the reaction-free energy be for cell growing at 37 Celsius? So 37 Celsius, we're going to want to convert that directly into Kelvin. So we're just going to add 273, which is 300 Kelvin. Okay, and this doesn't necessarily say that it's at equilibrium, so we're going to want to compute the Q value, which is related to K, as we'll see. The difference is that Q is the equilibrium, or sorry, the constant for the reaction when it's not at equilibrium. So just like above, we're going to take the concentrations and get our value for Q. And once we've computed Q, we're going to use the following equation: RT natural log Q over K. And the way we derived this was that we know that for delta G, let's see, delta G is going to be equal to delta G at standard conditions plus RT natural log K. My bad. Okay, and from up here, we're going to substitute. And using properties of logs, we can combine these two. And that's how we get this expression. So once we have the value of Q, we're going to use the above value for K, and then we should get an expression for the change in free energy at the given conditions. So question 5 tells us that an unknown buffer at 25 degrees Celsius at pH 7.5 is composed of 50 millimolar acidic form and 12.6 millimolar conjugate base. What is the pKa for this buffer? So what they're asking us is, or what they're asking us to use is the Henderson-Hasselbalch equation. Where, simply put, it's just going to be the base or the base. Yeah, this is the standard version in the acidic form. But the base doesn't always have to have a charge. For instance, when you're dealing with histidine is going to be uncharged, but then the acidic form is going to be charged. So that's just something to take into consideration. So we're going to plug in the values we're given after rearranging the equation, just putting the pKa on the left side. And we're given all these values. So the pH is going to be 7.5 minus the log of the acidic form, 6, 3. So it doesn't necessarily matter that this is in molar. What matters is that both of the concentrations are in the same unit, because the units will cancel out. We'll get a real number or a dimensionless number, so that we could compute the log, and that will eventually give us the pK, which is also unitless. All right, next part says, what commonly used buffer in a biological research lab might your unknown solution be? So if you look at the pK for biological buffers, we are going to find that it is tris. And you can refer to a table that has that information. Okay, so question 6. Inorganic phosphate is used in many biochemical reactions inside the cell as both a reactant and a product. Its concentration is therefore tightly regulated. How does a tenfold change of inorganic phosphate affect the change in free energy of any reaction it participates in? So let's consider the reaction we had above. Maybe put it this way, where the reactants we're looking at are GDP and inorganic phosphate, and then the product is GTP. So solving for the change in free energy equation that we derived above, we're going to have Q is equal to let's see, write the whole thing out. GTP, GDP, and inorganic phosphate. And then K is just going to be the same. But what we're going to do is that we are going to increase the concentration of inorganic phosphate by 10. And as you can see, whether inorganic phosphate is a reactant or a product is going to affect the change in free energy. So let's first try it out as a reactant. And I'll just make this KQ, and then Q is just going to be the same. But since we have inorganic phosphate in the denominator, we're going to be doing something like the concentration of inorganic phosphate initial is equal to 10 of the final, something like that. And then we're going to have 1 over 10 of Q initial. So using that, we're going to get 1 over 10 for Q and then K. And then we can break that apart using properties of log to our original change in free energy plus RT natural log of 1 over 10. 1 over 10, and it's just another property of log, is just going to be is equal to 10 to the negative 1. So just to be complete, this is also equal to RT natural log of 10. So as you can see, this is going to decrease the change in free energy and make the reaction more favorable. So when the concentration of inorganic phosphate as a reactant is increased tenfold, the reaction will now be more favorable. But if you were to do the opposite scenario, where inorganic phosphate is a product, so T natural log, and instead of 1 over 10, we're going to have 10 Q over K. We're going to do the same where we break it apart by properties of log. And now whatever value we had for the change in free energy is now going to be increased by RT natural log 10. And that's about 5.8 kilojoules per mole. I believe so. So what we can say from this is that when you have a tenfold increase in inorganic phosphate as a reactant, the reaction is now more favorable by about 5.8 kilojoules per mole. However, if inorganic phosphate is a product, it's going to be less favorable by the same amount. Question 7 says the pKa of a weak acid is 6. What is the pH when the concentration of the acid form is 0.3 and the concentration of the conjugate base is 0.003 molar? So right away, knowing that we're given the concentration for a conjugate base and the acid form, as well as a pKa or sometimes a pH, we know that it's going to ask us to solve the Henderson-Hasselbalch equation. Let's see. So this is the standard form. And we're just going to rearrange this. Again, like we did before, so that our pKa is on the left side. Okay, and then we're just going to plug in the values that we were given. So 6 minus the log of the acid form is going to be, let's see, so this is going to be the base and then the acid, and 0.3. Okay, and then you solve for that and you should get a dimensionless pK value. Question 8. Consider a protein with a surface-exposed histidine residue in a pH 5 solution. What is the fraction of protein molecules in which the histidine residue is protonated? Assume that the pK is 6. So we're given a pH and a pKa, and we're interested in the ratio of histidine and protonated histidine. So you might already be thinking of the Henderson-Hasselbalch equation. And you could either plug in values directly or rearrange it so that you're solving just for the ratio. But just to simplify the calculations, I'm going to plug in the values. And we should see that it's going to be pretty helpful. And this implies that, so 10, is that right? Yeah. Oops. So what I did is I took the anti-log. You might recall that 10 to some power of y is equal to log of x. Log base 10, I should say. So once you know the ratio, you're going to know, let's just say that the number that we get is going to be alpha. You're going to have the concentration of histidine is equal to some amount alpha of the protonated form. And the concentration of histidine plus the concentration of the protonated form is the total concentration, so that's going to be equal to 1. And you can substitute directly, so you're going to have, instead of histidine, you're going to have the following. You might make this alpha plus 1 of histidine plus. And then you can solve for the concentration of histidine. And then if you wanted to get the concentration of the non-protonated form, you just plug this value here and you would get both concentrations. I should probably state that you're actually not getting the concentration, you're getting the fraction of protein molecules. Apologize for that confusion. So next part is recent protein engineering work has found that the introduction of histidine onto the surface of proteins, such as antibodies, can enable switch-like behavior when the protein can exist in different compartments, such as the endosome, which has a pH of less than 6, and the cytosol, which has about physiological pH. So repeat the above calculation for pH 7.2. So same thing, just Henderson-Hasselbalch. And this is going to look like the following. And you're just going to use the same procedure to get the fraction of histidine and its protonated form. Okay, moving on to question 9. We have the following reaction, and we're given an equilibrium constant. A reaction is initiated at the following concentrations, and we're asked to compute Q. So one thing about Q is that for maybe a reaction A plus B goes to C and D, we're going to have the concentration of the products. Oops. And then the concentration of the reactants. And this is all the observed concentration, unlike the value for K, which is all the concentrations at equilibrium. So one thing that we have to take into consideration is that we also have the stoichiometric coefficients, and that is going to raise each concentration by its corresponding integer, or just coefficient. Let's see. I say that just because you don't always have to have an integer. But of course, it's a lot easier to understand when you're dealing with integers, like in the following. So Q is going to be equal to concentration of C squared, concentration A, concentration of B to the third, and you're just going to put in the values that were given, remembering to raise it to corresponding power. And then you should get a value for Q. And then you're asked, what direction does the reaction proceed? So if you recall, our change in free energy is RT natural log Q over K. And natural log is going to be negative if it's less than 1. And it's going to be positive if it's greater than 1. If it's 1, then our delta G is just going to be 0. And which makes sense, because if Q is equal to K, that means that this reaction is equilibrium, and at equilibrium, our change in free energy is 0. Okay. So when Q is greater than K, when Q is greater than K, we're going to have a positive number. So this implies that the natural log of Q over K is going to be greater than 1. And that implies delta G is going to be greater than 0. And therefore, this is going to be non-spontaneous. If Q is less than K, natural log Q over K is going to be less than 1. And the change in free energy is going to be less than 0. And that means that we're going to have a spontaneous reaction. So depending on the value that you get for Q and the value that you get for K, you can compare the two and determine whether this reaction is going to be spontaneous or not. Question 10. A histidine is involved in an interaction with the indole ring of an adjacent tryptophan that stabilizes the charged form of the histidine, such that the value of delta G for deprotonation is 5 kilojoules per mole at pH 7 and 300 Kelvin. What is the pK of this histidine? So we're going to use the following equation, and in this reaction we have histidine and its protonated form. So KEQ, oops, maybe put it this way. Okay, let's fix that. Histidine plus. So rearranging this equation, it's going to look like the following. And plugging in values, so we're given delta G. And since it's 300, we can do 2.5, or you could also do the gas constant times 300 Kelvin. And that's going to give us a value for KEQ. Then the pK, and this is the Henderson-Hasselbalch equation. It's going to be histidine plus. Okay, so we know that this is equivalent to KEQ. So I'm just going to substitute directly with the value that you get here. And you should get a value for the pK using this value for your KEQ, and taking the log of that and then doing 7 minus that value. And I believe it should be 7.869. Okay. Question 11. The T sub m of a protein is the temperature at which the change in free energy of the reaction folded species is in equilibrium with the unfolded species is equal to 0. Circle the best answer below. At the T sub m, the protein is 100% folded, 50% folded, and 50% folded. 100% folded, or 4, it is impossible to know with the data provided. So if you look how the heat capacity of a protein changes with temperature, it's going to be rather constant until it gets to some point where instead of Q, our heat going into the heat going to increase in the temperature, it's going to go into breaking bonds, and at which point it's going to be at a maximum when half of it is broken, half of the protein bonds are broken and half of it is unbroken, so 50% folded and 50% unfolded. And then it's going to go down, and it should slightly keep increasing. And this can be used to calculate the change in enthalpy for a protein. And this value in this entire scenario is important for drug design, but I will not be going into any further into that. Okay, question 12. A lysine side chain has 4 torsion angles, each of which can take on 3 different values. Each unique combination of angles is called a rotamer. For example, a lysine residue where the first, second, third, and fourth torsion angles are all 60 degrees is one unique rotamer, whereas a residue where the first, second, and third torsion angles are 60 and the fourth torsion angle is 180 is a second rotamer. In contrast, an aspartate side chain has only 2 torsion angles, which can take on 3 different values. assuming that all possible dihedral angles are allowed at each angle for residues at this surface exposed position. What is the difference in molar entropy between a protein with a surface exposed lysine and an otherwise identical protein with an aspartate mutation at this position? So we're asked to calculate the molar entropy, or the difference in molar entropy. And thinking back to multiplicity, if you look at the lysine, there are going to be 3 possible values that I can take on and 4 torsion angles. So that's going to give us a total amount of combinations of 3 to the 4th. So the multiplicity for lysine is going to be 3 to the 4th, whereas for aspartate, it only has 2 torsion angles. So there will only be 6 different combinations. So to calculate the change in entropy, the equation we were given previously is the following, which is derived from the statistical definition for entropy. And we can plug in the values we have, and you should get 18.3 joules Kelvin per mole. Okay, why might the simplification that each lysine torsion angle is able to adopt any of the 3 staggered positions, independent of the conformation at other torsion angles, led to an overestimate of the number of low energy conformations that lysine can adopt. So if you remember, maybe if you've taken organic chemistry, you can look down the bond of, let's just draw some organic protein. We're interested in this bond. And I can have something sticking out and then something behind. Now let's say we have something very bulky, like a butyl group. Then here we're just going to have hydrides. And then on the other side, we're going to have a hydroxyl coming out in front, and then hydrides elsewhere. So if you were to look at this right down there, maybe this is an eye looking down this bond, this would be most favorable when the hydroxyl is on the opposite side from the butyl, since single bonds can rotate. That's just because there's going to be less steric clashes between these larger groups. And it's not necessarily relevant when you just have hydrides, since they're not very large. So what I'm trying to get at is that there are going to be some conformations where there's going to be less steric hindrance, and this is not taken into consideration. So we can't say that each conformation or each rotamer is entirely independent from one another.